Okay, I I guess you can hear me now. We are live right now, and the comment section is working. By God's special grace, we are having a better output this evening. We we are right here for the lecture, Biomedical Electronics, MLS 321. Nice. I can see people commenting. If you are here in class, just identify yourself. You can comment and also put up your mat number and your name as a form of attendance. Thank you for being with us this evening for this important class. You are all welcome. I I guess your weekend is going on well, and I believe you've really enjoyed your weekend. So right now we have to start to ensure that we try to cover up some topics. After the lectures, we'll be taking questions. We also take class tests and assignments as the lecture is going on. So quickly, let's just say a word of prayer before we start. Dear Father, we thank you for giving us the privilege to convene this online lesson and class. Thank you for helping us put everything together, the devices. Thank you for the strength you've given us this weekend. Thank you for the wisdom and inspiration that you are giving us continually. We return all the glory and honor to you. As we commence this lecture, I pray that you help us achieve the needed outcome, that every one of us will learn and understand, and this lesson will be productive. Thank you for answered prayers in Jesus' name. Amen. Thank you, students. Quickly, let's move to our lecture for the day. Yes, I can see people commenting. I love that. As you comment, make sure you are commenting your name and mat number. So, last time we started definition of relevant terms in biomedical electronics and relevant terms, basic electricity concepts were discussed, and we were able to discuss the concept of electric current and voltage, and we also did exercises in defining these basic electricity concepts. Quickly this evening, we're continuing that lecture. We stopped at a point where we said that current is measured in amperes as well as voltage is measured in volts. Babe, current is measured in amperes. Just post. Okay. So current is measured in amperes and voltage is measured in volts. So quickly, I like us to take this down. That current is available in two ways. the alternating and the direct current. Current is available in two ways, the alternating and the direct current. What is the direct current? DC. This is the type of current that flows in one direction. Most small electronic devices will use direct current. Most mobile devices like your phones, your iPhone, your Android phone, cameras, they will get their voltage from a single cell, AA or AAA, triple A batteries. These cells typically generate about 1.5 volts DC. They are called direct current because they move in one direction. It does not change with time, and you could see that in the diagram of the flow of direct current. So that's the diagram for direct current. We say direct current is current that does not change with time. We could call that a figure 2.1. Okay. Now, quickly, what is the difference between direct current and alternating current? Alternating current AC, unlike direct current, alternating current changes direction with time. The AC allows for transmission of power efficiently over long distances. Now, in direct current, you don't transmit power over a long distance, so it travels through a short distance. But alternating current will allow you to transmit power efficiently over long distances. The alternating current varies with respect to time at a specific frequency. So you usually have alternating current within a frequency of either 50 hertz or 60 hertz, as the case may be. Now, where you talk about alternating current, you get short current from main supply, the kind of current that you get from the sockets in your houses or the sockets that are in the offices or in the laboratories is alternating current. You don't get alternating current from DC batteries. So it is easy to see that devices we plug into wall outlets uses alternating current. In Nigeria, main voltage is rated at about 230 volts at a frequency of 50 hertz, and that is it. For the positive half cycles, now the cycle or the diagram of an alternating current is a bit different from that of the direct current because it alternates. So it's in a sine wave form. So quickly, I just put that down as we move. So hmm? Hmm? Yeah. Okay. So that is the diagram for alternating current. You can see that diagram is represented in a sine wave, and then you could see the variation in voltage. So this is the kind of voltage that we get whenever we are talking about alternating current. Now, for the positive half cycles, current will flow clockwise, while for the negative half cycle, current will flow anti-clockwise as a function of time. That is alternating current. Now, it's very important that I need to know this concept, this very important concept, whenever you are discussing the difference between alternating current and direct current. This concept comes in so that you note that alternating current can be converted to direct current through a process that is called rectification. So where you have an alternating current, you can convert it to direct current. And how do you do that? Through a process called rectification. Rectification, I want to put it up. So that is rectification on the board. Rectification is simply a process, is a conversion of current that is alternating to a unidirectional current. And how do you achieve rectification? You achieve you achieve rectification. Please pardon, let me take this comment. I wish these network providers were a bit less frustrating. Okay, just try your best to find a space where the network will be easy for you to actually catch up. Now, thank you. Now, rectification is accomplished with set of diodes combined to form a rectifier. Rectification is achieved with a set of diodes. So that very statement introduces a component, you see, and we're going to that, but you now have a component coming, a diode. What is a diode? We'll get to know what a diode is and what the function of that component is as we progress. Now, but you achieve rectification by combining a set of diodes. When you combine a set of diodes, you form a rectifier, and then it can be used to convert current that is in alternating form to a unidirectional form, that is conversion from AC to DC. Some electronic instruments like the computers, display units cannot function with the AC in its form. So there are some components, there are some equipments you meet in the medical laboratories that cannot function with the alternating current alone in that form. So they require a rectifier to convert their AC supply to DC. Simple. Now I need you to take note of that. So at this point, we've been able to discuss effectively the current. Current in alternating form and direct form. So you can differentiate between current in alternating form and in direct form. So when you see the source, you identify it. When you see the form, you identify it quickly. Now let's move to another property that is very concept of current. We discuss the concept of voltage. Now we are heading resistance. Resistance. At the end of this very concept, I'm going to give you an analogy to unify these three basic concepts of electricity. So quickly we move to resistance. What is resistance? Quickly, I like to define resistance. Resistance is the opposition to the flow of current. It is simple. It can also be defined as the hindrance to the flow of current. So resistance is the opposition to the flow of current. Opposition to flow of current, or hindrance to flow of current, whichever way you want to put it. Now, the value of the intrinsic resistance of any material depends on some characteristics of the material. So, if a material is resistant, it depends on some characteristics. One is the length of the material, and three is the resistivity of the material. So I give you these three um, properties. You see those three determinants. You see those three characteristics of the resistivity of a material. The resistance of a material rather is determined by, first, the length of the material. Take it. Two, the cross-sectional area of the material. And three, the resistivity of the material. Let me quickly break it down. If you are considering using a wire as a resistance, for example, you could see that the longer the wire travels, the more the resistance. That's it. So you stretch it that it can travel through a longer distance. That's number one. Two, the cross-sectional area. There's an amount of current that will pass through a thin wire, and that wire will simply melt because the thickness or the area of the material is light. So it cannot resist the amount of heat or current that will pass through it. And then the resistivity of the material. Is that material more conducting, or is it more resistive to the flow of current? Now, resistivity is used to describe the extent to which a material can offer resistance. Therefore, it indicates the ability of a material to conduct charge. Materials with low resistivity value offer less resistance to the flow of charge and are better conductors. And materials with high resistivity values are not conductors. Such materials are referred to as resistors, and they are most times used as insulating material. The unit of resistance is ohms. Let me put that down. Now, don't forget the unit of electric current. Don't forget the unit of voltage, volts. Don't forget the unit of resistance, ohms. Electric current, ampere, then voltage, volts, and resistance, ohms. Very, very important. Now, quickly, let me give this analogy before I'll talk about the law that unites these three basic electricity concepts. Because whenever you talk about basic electricity and basic electronics, it must begin with these three concepts that we just defined. Now, this is the analogy of basic electricity and the synonym that describes how electrons flow in a circuit. Think about a water tap. Anytime you go to fetch water with a bucket at a tap, it gives you an idea or an insight about electricity. Where the water comes from a source, the water is generated through the sumo. That water can be likened to be the electric current, the electrons that are flowing, the water that flows into the bucket that you are fetching could be likened to be the electrons. Now, that water represents the electrons. There is a force that pushes water from the ground to the reservoir tanks and then to the distributing taps. That force that pushes this water from these various potential points is the voltage. And then you have the tap that helps you regulate the amount of flow of water. So why do you have a tap? The tap will help you restrict or hinder or regulate the flow of the electrons per se or water, and that is resistance. So you see this analogy, keep it with you, so that anytime you are defining the basic concepts of electricity, it can help you recall these things. Now, in physics, you don't discuss a concept without giving a backing law. There must be a law that backs up any concept in physics. So there is a law that backs up the concept of basic electricity in physics. Is called the Ohm's law and Joule-Hitting. Quickly, what is Ohm's law? The Ohm's law unites the basic quantities of electricity. The Ohm's law unites the basic concept and basic quantities of electricity. And Ohm's law states that current flow through a resistor in a circuit results in a voltage drop or potential difference across its ends. Let me repeat that definition. Ohm's law simply states that current flow through a resistor in a circuit results in a voltage drop or potential difference across its end. So, for current to flow through a resistor, it will result in a voltage drop. There will be drop in voltage, or there will be a potential difference across the 2 points. because the current is flowing from one point from the source to another point, and the point where it is flowing to will be the components. From the source to the components, that component can be either your phone, that component can be an appliance, that component can be a laboratory equipment, that component can be something that will absorb the current and the voltage that is generated from the source. So Ohm's law simply has a formula, a very simple formula that you can use to do a whole lot of calculations around basic electricity quantities. And that formula is simply V equals to IR. Now, as I put down this formula, I'd like you to magnet it on your mind so you don't forget. What is this V? This V stands for voltage. What is this I? This I stands for current. And what is this R? This R stands for resistance. We all know this. Good. Now, quickly, it's very important for you to also attach. I think it's very important for us to attach their units beside them for clarity. Now, voltage is volts, V, current A, amperes, and then resistance ohm. Get it down. Now, with this, there is a unique thing about this very formula. There's a unique thing about this very formula that I would like you to note at this point. This formula can be swapped into various things. Now, when you want to calculate voltage here, you simply calculate voltage by multiplying the current and the resistance. Now, what happens when you want to calculate the current? What happens when you want to calculate the resistance? So I wipe the board as we take it through different points. Then you could see how this Ohm's law can help unite the basic quantities of electricity. So we have this. So when you want to calculate I, you simply make I subject of the formula and divide the coefficient by the both sides. So I equals to V over R. Then when you want to calculate the resistance, R is equals to V over I. So that is it. Simply, you see, this Ohm's law has been used here to split, and it can be used to calculate these properties separately. Now, quickly about resistance, we say that resistance increases with temperature. Take note of that. Resistance increases with temperature. When an electric charge flows through a resistor, some of the electrical energy is transferred to heat energy, and the resistor gets hot. This heat causes the ions in the conductor to vibrate more easily, and this heat also, it makes it more difficult for charge carrying electrons to get through the material. So current can flow easily when the resistor is increasing. So when you want to restrict current flow, you increase the resistor or resistance in the circuit. So quickly, I like to give us a question so that we can solve immediately to try to understand the use of this formula that I just gave. Let me call it example 1 today. Example 1. Now I want you to try out that exercise yourself while we are also getting ready. I want you to try that exercise yourself while you are getting ready. Let me repeat that question. That question. Hope you can see the board very well. Do you have any issues with the board? Please, can you see the board very well? You comment so that I would know actually if the lecture is flowing. That question says a voltmeter V reads 6 volts and a resistor R is 4 ohms. What is the current through the ammeter A? You see. What is the current through the ammeter A? Someone should look at those three formulas that we got from Ohm's law. Which one will be more appropriate? Someone said that the board is looking blurred. Okay, that he or she can't see clearly. Okay, I think you can see clearly now. I think you can see clearly now. You please. I think you can see clearly now. So you see, which formula among these three do you think is more appropriate? Cool. Thanks. The person said can see clearly now. Now, which formula do you think is more appropriate? Which formula do you think is more appropriate to solve that question? A voltmeter V reads 6 volts and the resistor R is 4 ohms. What is the current through the ammeter? You see, who can just suggest which formula do you think is more appropriate to solve that question quickly before you start solving? V equals to IR, I equals V over R, and R equals V over I. While I wait for your response quickly, and let me say this. Now, it is very important for us to note that materials that allow the flow of electric current, differs, and they don't allow it in the same degree. So that leads us to another very important topic: classification of materials. Classification of materials. I think you have taken down the question. Let me wipe the board so that I will come to it. I'll come to it quickly. Or do we just solve that question so that we go to something else? Okay. Without wasting much of our time, you can see that here voltmeter V reads 6 volts. So the voltage is given. And resistor is 4 ohms. So we are asked to find the current. The current is this. The proper formula to use is the middle one, I equals V over R. So what do? You simply substitute 6 volts here, and then you substitute 4 ohms there. So that gives you, I wipe this now, I remove this, and I also remove this. So we are left with I equals to V over R. So we have 6 over 4, and that should give us 1.5. 1.5 watt. Since this is current, you must write the unit 1.5 amperes. I think that's the solution. Quickly, and we move. So at this point, let's wipe the board and go over to classification of materials. Classification of materials. I think um, before I move to classification of materials, I almost skipped Joule heating. Any resistor will cause electrons to be scattered from the current flow. As the electrons are scattered, they dissipate energy in the form of heat, and this is called the Joule heating. Now, the power associated with this loss of energy as a result of heat is it can be called power. P equals to IV or I squared R or V squared R. P equals to IV or I squared R or V squared R. So this is the power that is associated from heat that is lost as a result of flow of electrons through a resistor, and that power can either be calculated using this formula P equals to IV or I squared R or V squared R, and that is Joule heating. P there is the heating power that is measured in watts. All right, that's take down that information while we move quickly to classification of materials. Um, I don't. Do I have any question? Do I have any question as regarding this before we move quickly? Do I have any question? Someone said that I'm not seeing the board, but I've tried to make the stuff close to the board. So I think try your best to see. Try your best to see what is written on the board. Quickly, let's move to classification of materials before we get into electric circuit and electric circuit components. Materials